Okay, let's start. Welcome everyone to our ZAC seminar. It's my big pleasure to introduce Marta Pieropan from University of Utrecht. And Marta will speak about Campana points on Fano varieties. Thank you, Marta.
Yeah. Thank you very much. Thanks for inviting me to give a talk in this very important international online seminar. I will talk about Campana points on Fano varieties over number fields, arithmetic aspects of them. I believe that you have heard another talk about Campana points very recently. So this will be, I guess, a different point of view on the same topic. Well, I will start with introducing all the objects. So let's start with some notation. I want to fix a finite extension of the rational numbers, also known as number field. I also want to fix the ring of integers, which is the integral closure of the ring of the integer numbers of Z in the field K. And in case here in the audience we have people who only work with complex numbers or so, if you are not familiar with number fields, just think of K equal Q and OK equals Z. That's a good example and it's good enough for this talk. All right, so the setting I want to work on is the following. I look at X, some smooth projective variety over K. And I want to consider inside X a divisor, which is reduced and strict normal crossing. And since I want to play around with my divisor, I'm going to write down the decomposition into irreducible components. So it is a sum of irreducible divisors, di's. Let's keep my indices as my notes. So this is a sum 1 to S. All right, so in order to talk about Campana points, I need an integral model over some, well, over the ring of integers, or maybe I cannot find a nice, suitably nice integral model over the ring of integers, so I will work with some open subset. So I will have my curly X, an integral model over some open subset of the spectrum of the ring of integers. And remember that we have this map from spec K, which is nothing but the generic point. So the generic fiber of my curly X is going to be X, my smooth projective variety, and I require that curly X is regular, and that the morphism, the structure map to spec R, is flat and proper. And here spec R is just an open subset. And now that I have my model, I'm going to consider here inside a divisor, curly D, which is nothing but, if we look, this is the composition, so it's a sum 1 to S of the i's, and each of my curly di's is just the Zariski closure of the di's in curly X. So just like this, I get a model of my divisor T. All right. So now that we have our setting, I want to talk about first rational point and the integral points, and then finally we will introduce Campana points. Okay, so what's special about this setting is the fact that the ring over which I'm working, the ring R, but also the ring of integers OK, is the Dedekind domain. And I'm going to introduce Campana points in this setting because it is the setting for the applications that I have in mind. But you can introduce Campana points whenever you have something of this type over any Dedekind domain R. So you just have some regular scheme, flat proper. The generic fiber is smooth projective over the function field. And then you have some divisors such that the generic fiber is reduced and strict normal crossing in the generic fiber of curly X. Okay, so the first thing to recall is that since curly X is proper over R, then if we look at integral points, so R points of curly X, this set is just the same as K points on straight X, rational points, K points on the generic fiber. And this is just our properness. But now I'm going to look at points into the complement of D in my divisor, or in my variety and in my model. And so if I look at any point X to curly X, any R point, then I want to look at the ideal, which is the pullback of the ideal that defines the divisor curly D. And this is an ideal sheaf over spec R, but we can look at this as an ideal of R. All right. So now I want to look at properties of the point X and the corresponding ideal in R. The first property is that we know that the point X is a point in the boundary D, if and only if, well, the pullback of this ideal is the zero ideal in R. And then if the point is not a point in my boundary, which is equivalent to say that then the pullback of the ideal is not a zero ideal. So we have a non-zero ideal in our Dedekind domain. And then by unique factorization of ideals, in the Dedekind domain R, then I can write my ideal pullback of the ideal that defines D as a product over all primes, well, non-zero primes, of P to the order of our ideal with respect to the prime P. This is just the algebraic way to write down where I'm taking the pullback of the divisor D, and it is not the whole space because the image of my morphism X is not all contained inside D. Okay, so once we have this, then we can try to understand when is my point X in the complement of D. So I look at R points in the complement of the boundary, and then my point X belongs there if and only if, well, if and only if when I pull back the divisor D, then I get a zero divisor in spec R. All right. But this, if we look at our characterization of the pullback of the ideal sheaf, this is equivalent to saying that the order of the pullback of the ideal sheaf at P is zero. for every choice of my non-zero primes P. Okay, so this is all to say that we can have this characterization of integral points with respect to the boundary D in terms of valuation with respect to the prime ideas of R. And in particular, we see from this that if I look at my set of integral points in the complement of D, then this is contained in the set of integral points on X that are not integral points on the boundary, but this inclusion is a strict inclusion whenever D is a non-trivial divisor. And on this right-hand side, this difference by properness is nothing but the set of K points, K rational points on the complement of D. All right, so let me see here. Yeah, we have all our examples in blue. So let's look at one example just to make this very concrete. We have X, projective space. So R is Z, and I choose as my boundary just a hyperplane, x0 equals 0. And then I can consider some points, for example, 2, 1, 1. The first coordinate is 2, all the other coordinates are equal to 1. And then I see immediately, okay, this is not a point in the boundary because 2 is non-zero. But if I reduce this point modulo 2, then this becomes a point in the boundary. And this tells me that this is not an integral point in the complement of D. And this, okay, you can see it as an example to substantiate the fact that we have a strict inclusion between integral points in the complement of the boundary and integral points that are not contained in the boundary. Those are two different things. Okay, so this is the little recap on rational points and integral points. And why do I want to do this? Well, because I want to talk about Campana points, and Campana points are an intermediate notion. I will talk about sets of points that lie in between this set and the bigger set. I will just put something in there in between, and these will be sets of Campana points. So here we go. I'm going to talk about KLT Campana points. So to define Campana points, I need some parameters. So I'm going to fix M, which is an S tuple of integers, M1 up to MS. These are going to be positive integers. And attached to this M, I'm going to write down the corresponding divisor with standard coefficients based on the reducible components of D. So sum 1 to S of this. DI's with coefficient 1 minus 1 over MI. Then we say that the pair X dm is a KLT Campana orbifold. Okay, so this is the geometric object we want to play with, but to define Campana points, I will have to use models all the time. So this gives me all the data that I need, And now I can define the set of KLT Campana points as follows. So I will call it set depending on curly x, curly d, the parameter m, and then r. These are r points on curly x. So an r point x is a Campana point if for every component di and for every non-zero prime of spec R, then if the order at P of my ideal pullback of the ideal sheaf of D is positive. So if when I pull back my divisor D, I get a DI component with a positive coefficient, then I impose that this coefficient is big enough. Which means at least MI. Okay. So this is not the most general definition of Campana points that one can give, and actually people can also discuss about different definition of Campana points. In particular, I did not consider the case when I allow myself to have a reduced component here, so with coefficient 1. If you want to have the most general definition, you can add here the, well, I write this in blue, so you can add here the possibility of, well, formal possibility of having mi equal to infinity, which just means that the coefficient of the I in this sum becomes 1. And then if you do that, you can modify the definition of Campana points by requiring what we have required only in the case where mi is an integer, and for all the other components, then what we require is simply the integrality condition. So that the order at P of the I is 0 for every prime P. In particular, from this definition, this may be not so apparent, but if mi is in Z, we allow the points to be contained in the boundary or in the boundary components. And if they are not completely contained in the boundary components, then if they do intersect the boundary component, so this condition, then they have to intersect with high enough multiplicity. And you could call this as you could look at this as a tangency condition. But if you have here some coefficient 1, then you just require the points not to be contained in the boundary, and you require the point to actually satisfy the integrality condition with respect to the boundary component. Okay, so this is my set of KLT Campana points. And now I'm going to relate this to rational points and integral points. So let's see. Points that are in the complement of the boundary, so integral points with respect to our boundary, there are always Campana points for every choice of parameters mi's. Also, all Campana points are rational points. So we're really not inventing anything new. We just select some rational points with special properties and we call them Campana points. And we have equality here with the set of rational points if and only if we choose mi equal to 1 for every I, because in that case, the condition that I'm requiring here this condition, well, the second part of the condition becomes a trivial condition. If a number, if an integer is positive, then it is at least 1. That's what it becomes. So it really doesn't add anything. Okay, I just noticed that because I'm using this definition here, I should be more precise. So here we are not looking at rational points in the complement of the boundary. As I was saying before, we allow for KLT Campana points to lie in the boundary. So we really have to look at all points on curly X. This is precise. And the next thing that I want to say about this is that look at what happens if we take the intersection of all possible sets of Campana points for all choices of parameters. So what happens here is that we get the condition that whenever I have a coefficient which is positive, then the order or the coefficient has to be at least mi for every choice of mi, and mi can be any integer. So this says that I have some integer that has to be bigger or equal than every other integer, and this is not possible. So it means that we never have this condition. And now, because I allow myself to have KLT Campana points in the boundary, I guess that to be precise here, I also have to add the points in the boundary. So this thing of asking the points to be in the boundary or not being the boundary is something that has some arithmetical consequences that maybe I can talk about later. But if you require just from the start for your Campana points to just never be contained inside the boundary, which you can do, then you can look at this set and you recover precisely the set of integral points. And so when people say Campana points interpolate between rational points and integral points, or between integral points and rational points, what it really means is that if you choose your coefficient in the right way, then you really get back the set of rational points. And okay, if you allow yourself for integrality conditions to be part of your definition, then you don't have KLT Campana points. We call them DLT Campana points, or you just call them Campana points, and that's all right. So you can also realize the set of integral points as a set of Campana points. But even if you don't allow that, if you just look at this restricted definition of Campana points with the KLT condition, so ignoring the blue parts that I've written here, then in that case, you never describe the set of integral points as a set of Campana points, but you recover such a set and such conditions when you take the intersection of all of them. Okay, so now I want to talk about Campana points and Fano varieties. I will start with the potential density conjecture. And if what I've said so far is mostly true for any Dedekind domain, now we really want to look at Dedekind domains that are, well, possibly localizations of rings of integers of global fields, for example, number fields. So if now I restrict myself to X smooth projective Fano variety, or if you want, you can also require this to be rationally connected, or even Calabi-Yau type. Then it is expected that up to taking a finite extension of the base field is K, Then we look at the set of rational points over this extension K prime, and this is Zariski dense in the variety X. This is the classical potential density conjecture for rational points. And we have an extension of this conjecture to Campana points, which is due to Campana himself. Which says that if the pair XDM, the Campana orbifold, is log Fano, then we expect potential density for the set of Campana points. It doesn't have to be log Fano, it suffices that it is special in the sense of Campana's definition of special variety. So to be precise, we expect that up to taking a finite extension of the base field, then we can look at the set of Campana points with respect to this extension, which means that we're looking at the integral closure of the ring R in the extension K prime, and we expect this to be Zariski dense in X. I'm looking at this over R prime because I want to define Campana points, but they are all also K prime points on X. And so when I look at density, I really only look at density within the projective variety X. This is well defined. And this is the setting where I usually work. My work is about the distribution of rational points or Campana points on variety that satisfy the potential density conjecture. This conjecture is open. The classical conjecture for rational points is open. The conjecture for Campana points is also even more open because we have much fewer results in this new setting. But if I assume that my variety satisfies this potential density conjecture, then I have some way to predict how my points are going to be distributed, and this is what I want to talk about in the second part of the talk. So first, I want to make clear what I mean by distribution of rational points and how do we measure this. So I'm going to briefly recall heights. So recall that the Weyl height is a function from the set of rational points on the projective space, and I'm just going to write down the actual definition when the field is the field of rational numbers, because it is much easier to write down and to understand. So it is an R-valued function with positive image. And whenever we look at the point with integer coordinates, then the height is the maximum of the absolute values of the coordinates. And we have to normalize this by dividing by the GCD, or if you want, you require at the beginning that the GCD of the coordinates is 1. It is always possible to do that, and then you just have the maximum of the absolute values. All right. So now if I take, say, for the sake of this talk, I'm just working with very ample line bundles, but you can do, you can define the height also if your line bundle is only big. So I have my smooth projective variety X. I take, say, a very ample line bundle, and then I can define a height induced by L on the set of K points as follows. I'm just going to look at Well, in this case, the embedding or some map to the projective space induced by the linear system, the complete linear system of L. And then I compose with the veil height. And the veil height is defined for every number field. Okay, so this is one way to define heights. It works very well, it's very geometric. And when I define height this way or in any other arithmetic way, when the divisor I use or the line bundle L I use is at least big, then I have the Northcote property, which says that if I fix some bound and I look at rational points of L height at most my given bound, then this is a finite set for every choice of B. And this is true if L is very ample. If your divisor is only big, maybe you have to work in some open subset of X, because you don't want that something here is contracted by the map. Or maybe your map is not even defined on the whole X. Anyway, now comes the problem that people in my research field usually look at. And the problem is the following. Given some subset of the set of rational points, say U, which is dense in the variety X, because if it is not dense, it means that its closure is a closed subvariety of X, and then maybe I should look at the closed subvariety and not at X itself if I want to understand this set of points. Then the problem is to determine the asymptotic behavior of the following counting function. And the counting function NUL of B is the function that counts points in U of bounded height. And because we have this Northcote property, and we are looking just at some subset of the set of rational points, so this is always a finite set. And so, okay, and ULB is going to be the cardinality of this finite set. So we get a number, and this is a function of B. So we want to understand the asymptotic behavior of this function. Well, we would be very happy to understand the function by itself, all the values, but this is very difficult. So we want to understand the asymptotic behavior for B that becomes very large. So this is the type of problems. And one solution, at least for Fano varieties or varieties of Fano type, is the Manning's conjecture, which is, well, a bit old by now. And what I'm going to write down is not the Manning's conjecture as it was at the beginning, nor the refinements of the Manning's conjecture. What I'm going to describe now is a generalization of this Manning's conjecture to the setting of Campana points. And this is in joint work with Arne Smits and Sho Tanimoto and Tony Barilli Alvarado. And the paper is on arXiv since 2019. All right. So the conjecture says the following. If my Campana orbifold XDM is log Fano, and really here I'm looking only at the KLT setting. I'm going to write it here. We don't have a conjecture in the most general setting. So if I have a KLT log Fano pair, which is also a Campana orbifold, and I know that the set of Campana points with respect to some nice model curly X over some suitable open subsets of my ring of integers R is dense in X and also not thin. So here I will have to open a small parenthesis about this notion of being thin. It is a notion which has been introduced by Serre, and you may have seen already a number of times in this seminar. It means that the set is contained in a finite union of proper closed subvarieties or finite union of images of certain generically finite maps. So images of rational points under such map. And maps such that they are not birational. Okay, so this is the setting. We don't want our set of Campana points to be contained in a finite union of proper closed varieties or images of rational points under generically finite maps of degree at least 2. And we fix an ample line bundle or a big line bundle, or as I write it here, very ample, just to be consistent with the rest of the talk, so that we can define a height. Then the conjecture says that we can find some suitable exceptional set Z contained in the set of Campana, in the set of rational points, which is small enough, and small enough means it is thin, it is contained in a thin set. And the role of this is that if we count points outside of this exceptional set Z, so I look at Campana points, which are not inside Z, and of bounded height, then I can give a precise prediction of what this counting function is supposed to do. And the prediction says that asymptotically, this function behaves as some constant C, positive constant, times b to the a times log b to the power b minus 1, where a and b are the following geometric constants. A is the Fujita invariant of my orbifold with respect to L, more precisely the smallest real number such that TL plus the canonical divisor plus the M, so plus the log canonical divisor, is effective. And B is the codimension when we look or we work in the, well, the Néron-Severi group if you want, but we are in the Fano case, so the Picard group as a vector space. And then it's the codimension of the minimal face of the effective cone that contains the adjoint divisor given by A. So the minimal face of the effective cone of X that contains my divisor AL plus the log canonical divisor. Good. So what we see from this precise description of what A and B are supposed to be, well, we see that A and B are geometric. In some sense, they only depend on the choice of X. They certainly don't depend on the choice of the model, curly X. The constant C in front of this, well, the leading constant in this asymptotic formula instead contains all the information that comes from the model X, the choices that are involved in the height associated to the line bundle L, and, well, the associated choice of the model, of the boundary, and so on. And the other thing that we see here is that also these not only A and B not only don't depend on the choice of the model, they don't even depend on the choice of the open that we are considering. All right, so now that we have the conjecture, I would like to spend a couple of minutes on the results about this conjecture. So I have prepared it here because otherwise it's too long to write. So these are results on Manning's conjecture for Campana points that we have so far. I did not put anything about the Manning's conjecture for rational points. There is a huge literature about that. I have worked on that as well. So that would be good for another talk. But for Campana points, we have the following. So before we even stated the conjecture, a few people have been working on similar problems without calling them Campana points necessarily. So we do have a couple of results from 2012 related to the thesis of Van Valkenburg, student of Tim Browning. And these are about what happens if X is a projective space and we choose this special boundary, all the coordinate hyperplanes plus one more coordinate hyperplane defined by the sum of the coordinates equal to 0. And this is a conjecture. So what Van Valkenburg does is prove an asymptotic formula for the given counting, the same counting function as in the conjecture. And so he shows that the conjecture holds in the case when the dimension of the projective space is at least 3, so n is at least 5, and all the multiplicities, so the parameters mi's are equal to 2. What remains open then is the case when n is equal to 4, and the case where n is equal to 3. N equal to 3 corresponds to P1, and we have a result by Tim Browning and Van Valkenburg, which is just some lower bounds and some upper bounds for our asymptotic formula. And this is an open problem, which is actually possibly a little bit older, which is still open because this counting problem is extremely difficult to deal with in number theory. So what we have instead more, so we have a generalization of this result by Van Valkenburg to say arbitrary parameters, as long as there is some condition here, this condition is equivalent to a condition on the dimension somehow. So we have a recent paper by Tim Browning and Shuntaro Yamagishi on this. And then since the conjecture was stated in the same paper where we state the conjecture, we also show that the conjecture holds for smooth equivariant compactifications of vector groups with respect to an equivariant boundary. And in the joint work with Damaris Schindler, we show that the conjecture holds for, well, a lot of split toric varieties over Q with, again, equivariant boundary and with the choice of an log anticanonical divisor. And then I wanted also to mention the most recent results. We have a result by Xiao, a student of Shota Nimoto, where he extends the techniques that we use in the paper about equivariant compactification of vector groups to be equivariant compactification of the Heisenberg group over Q. And then we have also a nice paper by Sam Streeter, student of Dan Lohran, which is now, this is the first example that we have of a different type of boundary. So we have a projective space here and some boundary, which is defined by a norm form. Well, the norm depends on some extension of degree D. So this does not necessarily fit the setting of the conjecture because the boundary is not a strict normal crossing divisor in general, but we have an asymptotic formula for this kind of counting. And the type of points are defined in the same way as Campana points, and I think that they call them something like generalized Campana points or so. And then more, well, at the same time, Sam Streeter has been working with Nakahara on what can we do about the thinness of the set of Campana points. And so the result that they prove, which is analogous to a result that we have for rational points, is showing that weak approximation implies that the set of Campana points is not thin. And this is quite important. And then even more recently, we have a couple of papers that have appeared on arXiv in the last month or so. And then we have the first paper that solves the problem for n equal 4 in the setting that I was mentioning before. So in this setting of von Valkenburg at the beginning, and again with multiplicities all equal 2. So this is one thing that we have right now, and the conjecture holds in that case. And also Alex Schutt has also a different paper where he tries to understand how the leading constant on the asymptotic formula, the constant C, can depend on how and which thin sets we remove. And that's also a very interesting paper. Okay. So now that we have seen essentially a summary of the literature, I want to say a couple of things from the paper with Damaris Schindler. So here we talk about toric varieties. We treat toric varieties with a very different type of technique than the one used for this equivalent compactification of vector groups. So for vector groups, we use the so-called height zeta function method, and we expect that the same method holds very well for all toric varieties over all number fields with respect to all possible heights. With the Damaris, we proved a different technique on toric varieties. And one nice thing that came out of that is some sort of combinatorial motivation for why the exponents, I have it in the other slide, why the exponents A, B, and B are supposed to have this description. So this is what I want to say in the last 10 minutes. So what I'm talking about is some heuristic that comes from the analytic number theoretic technique that we use for counting. And the setting where we work is the following. So we have a toric variety over Q, and then we look at the Cox ring of this variety, which is just a polynomial ring with n variables that corresponds to the rays of the fan that define my toric variety. And here inside, I have the global sections of the line bundle that I use to define the height. And I can write this as a vector space generated by some sections. And these sections are all monomials. So I write here as I can be written as a product of the variables we have with just some exponents. So I'm just saying that we can always find a basis that looks like this. And then what we want to do after some manipulations, we want to count integers, x1 up to xn. You can say even positive integers, such that each integer xi is so-called mi full. I'm not going to go into the definition of what this is unless you ask me later, but it just encapsulates the Campana condition with respect to the boundary component di. So here I didn't write, but my boundary is the union of the toric invariant divisors of X. And I want to count Xi with this property of size B to the Ti, which means that I'm counting in some intervals B to the Ti, B to the 2Ti. So this is the idea behind the method of counting that we use. And also we want that S1, SR for this is at most B, and this is the height condition. So what we are doing somehow, we are taking the area where the domain in space where we have to count points, and that's just given by this condition of the height. We want to count points of bounded height. We can parameterize our points so that all coordinates are going to be integers, and we can also reduce to the case of positive integers if we want. So we're counting points in lattice, and we want to count points in the lattice in some region with some Campana condition. What we do is that we cover the region where we want to count points with boxes. So we intersect them with boxes of, roughly speaking, this type. From B to some power to B to some other power, where we have some parameter in the power that we are going to adjust as we need. So we just want to count in boxes. And then whenever we count in one of these boxes, then we get a counting which is, roughly speaking, B to the sum Ti divided by Mi, because I'm counting points of size B to the Ti, and if my box is already contained completely in the region where I want to count, then I'm just ignoring the height and I'm just counting points with this M-fullness condition and this, say, size of Xi up to this B to the Ti. And so, okay, you can do this count and you get this kind of function. So what we want to do now is to understand which of these boxes contribute to the main term of my formula, of my asymptotic formula, and which boxes don't contribute. They are just going to hide in the error term. So to do this, it means that I want to see for which boxes, so for which parameters Ti, the counting, the resulting count, so this B to this power is going to be bigger than for other boxes. It's going to be the biggest. So what we want to do, we want to maximize this function. And we want to maximize this function, which is equivalent to maximizing the exponent. This is a linear function in Ti. But we also want that the box is contained in the region where I want to count. So I have some condition. And the conditions look like this. Sum of alpha ij's Ti, I from 1 to n. For every j from 1 to s, I have one for each of the sections. And this is the height condition. And I also want my Ti's to be non-zero. So what happens is that I have these two linear conditions. Oh, I forgot. So the first condition is the sum is at most 1. I'm just rewriting Si in this form and writing that the condition is that Si is at most B. And B, okay. B is B to the Ti in this case. So the upshot of this anyway is that these two conditions that we have here, they define a polytope, a bounded convex polytope in R to the n. And the type of problems that we have maximize this linear function on a polytope is a linear programming problem. And now there is a result from linear programming that says that solving a linear programming problem is equivalent to solving the dual linear programming problem as long as the solution is non-negative. And what we do is then we write down the dual linear programming problem. And we see that this dual linear programming problem is a problem in the geometry of the toric variety, and we can actually solve it. It has solution precisely the exponent A of B in the asymptotic formula. Exponent A, which is given by taking the infimum of T such that this whole thing holds. We write down a basis of the Picard group. We write down this condition in the Picard group. We have a minimizing problem in this case, which is dual to the linear programming problem that comes from this wanting to count points in this way. And this way means the hyperbola method for counting rational points. So once that we have this from the hyperbola method, we also get that if we can run it, then we expect to obtain an asymptotic formula, which is some constant, which is not explicit in principle, then b to the a times log b to some power k. And now here k in this case is the dimension of the phase of the polytope P, the one defined by these two conditions from the counting problem, where the maximal value of the function that we want to maximize is attained. But now that we do have this setting for the dual linear programming problem that already we know gives the right answer A, then we look at the toric geometric setting, and we figure that indeed this gives us that k has to be equal to b minus 1, the prediction from the conjecture. So this is what we get. We get a conjecture which has also some geometric reasons behind, and it is modeled on the case for rational points. We also have this heuristic that comes from this hyperbola method that when we did run it on the case, in the case of toric variety, it repeats the conjecture. So it gives the same expectation as the conjecture. So somehow it confirms it in the sense of, well, there is one other, in this case, analytic reason why we should expect the asymptotic formula to look like this. And well, this is what I wanted to present today. So I think I will finish now.
Thank you, Marta. Let's thanks Marta. Okay, thank you very much. It was very nice. Questions? I have general questions like basically your technique. To which other Fano orbitals you plan to apply it?
This hyperbola method technique?
Yeah, and
So, well, in combination with some other methods, I know that a student of Damaris is trying to work out the case of some sub-varieties of toric varieties, non-toric ones. And then the other thing that we want to do next is try to apply this to a non-toric boundary. So this method doesn't use the toric structure. It plays very well with the toric structure because it is very well understood and very regular in a sense, but it doesn't need the toric structure to work. And so in principle, it could be applied to other cases. However, we don't have other results at the moment.
And for example, for varieties with torus action of complexity 1?
Yeah, that's more complicated.
They almost toric in some
Possible to
sense.
try to do something. So there is one part here which is hidden because I didn't want to go into details, but how to transform the original counting problem into counting something that comes from the Cox ring. This is called the torsor method or the universal torsor method, on which I've been working as well. And that actually works also in some cases where you are looking at torus with an action of complexity 1. So Giuliano Gagliardi and Ulrich Derentala have a paper about that.
Okay. Okay. Any other questions to Marta? Okay, so let me check. There's nothing in the chat. Okay, so if there are no more questions, let's thanks Marta again. Thank you very much.
Thank you.
Okay, Marta, thanks. I will upload the video in the evening today, a little bit later. Yeah, thank you very much. It was very nice talk. And when pandemic is over, hope to see you again, maybe in Edinburgh, like last time.
Nice.
Yeah. Okay, or maybe in Netherlands.
Yeah, as well.
Okay, thank you. Okay, thank you. Bye.
Bye.
Bye.